All right, so hello everyone and welcome to the European Non-Associative seminar. Today's speaker is Petr Vojtěchovský from the University of Denmark. He's going to speak on solvability and nilpotence, just beyond groups. Please.
Okay, well, thank you very much for the invitation to talk at the seminar. I think this is a slightly different talk than most of the titles and abstracts I've seen posted on your website, in the sense that I do work in non-associative algebra, but it's mostly algebras with a single binary operation. So it's not a vector space with two operations of addition and multiplication and their interplay, but rather just a single binary operation that's not associative. But you will see that there is still a lot to explore, and it leads to interesting mathematics. It's resembling group theory, but it's more complicated than group theory. So this is a project on the concepts of solvability and nilpotence, just outside of groups. And it's a joint work with Drapal and Stanovsky, and I'm emphasizing the initials capital D and capital S. If you see that in the talk, in some attributions of theorems, then it means it's attributed to them. And here is just an outline. I will not read it, but we'll start with the classical solvability and congruence solvability to show that there is a subtle difference between these two theories, and the congruence solvability theory that comes from universal algebra happens to coincide with solvability in groups, but not in general. So the general theory is based on commutators of congruences, and this is a theory developed in the 80s. Can you hear me? I just got a notification that I got muted. But,
Yes, now I can hear you.
Okay, very good. So this is a theory developed by Fries and McEntee in the 80s for congruence modular varieties. So let me say a few words about this, because I do not expect that necessarily everybody has background on universal algebra. But you've probably heard of congruences. So a congruence on an algebra is an equivalence relation that respects, or it's compatible with the operation. So as an example of the equivalence with a binary operation, if x is related to x prime and y is related to y prime, then the product x prime has to be related to y prime. And this must hold for all xy in the algebra and all operations. And if you look at these congruences, there's the largest congruence, everything, and the smallest congruence, just the diagonal. And just to explain the modularity, what does it mean to have a congruence modular varieties? Well, if the lattice of congruences is modular, which is the implication posted here at the bottom, then it's a congruence modular variety. And in these varieties, the theory applies. And here's the key definition that tells you when two congruences commute. So the notion is, if you have three congruences, alpha, beta, and delta, and I will illustrate it with an example quickly, then if this implication holds for any term, then you say that alpha centralizes beta over delta. And what is this implication? Well, it basically says if you have some arguments x, u, v, and y, then if the u and v arguments are beta related, then you can replace the x with y, which are alpha related, and the outcomes will still be delta related. So it's a little bit difficult to read, but just or to immediately understand what it says. But just notice that certainly if delta is everything, means the full congruence A times A, then this implication is trivially satisfied. So it's harder to satisfy it for small congruences delta. So the commutator of alpha and beta, which are two congruences, will be declared as the smallest congruence that satisfies this implication. And let me give you an example from group theory so that we get some idea how these things work. So take a group and take this particular term. It has to be true for all terms, but let's consider the standard commutator term, x2 minus 1, y2 minus 1, xy. And now we have to have some congruences, but in groups, of course, congruences are in one-to-one correspondence with normal subgroups. So I'll just take a normal subgroup A, and the cosets are the equivalence classes of the corresponding congruence alpha. And similarly, another normal subgroup B, and the cosets determine congruence beta. And now for the setup of the implication in the term condition, suppose that X is 1 and it's alpha related to Y. In other words, Y is an element of capital A, and U is 1, beta related to V. In other words, V is an element of B. So now the left-hand side of the implication is satisfied for any delta, because TXU is just T11, and of course that collapses to 1 as a commutator term, and similarly TXV is just 1. So these must be related because the diagonal is always contained in any congruence, and therefore the right-hand side, TYU, has to be delta equivalent to TYV, but TYU still collapses to 1 because U is 1, so the commutator is 1, but TYV no more collapses, and it is the commutator Y2 minus 1, V2 minus 1, YV. So what this little calculation shows, that in the commutator of the congruences alpha and beta, you have to find all standard commutators. And it turns out that there's nothing else, but one has to come up with some argument. So in case of groups, no matter which term you use, you will not pick up anything else than these commutators. So this calculation shows that the standard commutator of normal subgroups is contained in this congruence commutator of congruences, but in fact for groups they coincide. And I will say a little bit more about it later. But once you have this setup of commutators of congruences, you are in business for solvability in exactly the same way as in group theory, where you can define the derived series. So here is an example of the derived series. You start with the largest congruence, and then of course you iterate the commutator. And if you reach the smallest congruence in finitely many steps, it's a solvable algebra. Now, let me specialize to what I will mostly talk about, which is an example of a non-associative algebra with a single binary operation, despite the fact that I'm listing 3 operations here, which is for the purposes of a universal algebraic point of view. So what is a loop? Loop is an algebra with an identity element, and such that basically the left translation by X is a permutation of the underlying set. Okay, so, and similarly, the right translation by X is a permutation of the underlying set. So all the translations by Jack. And that means that you can multiply on the left by X, and you can also divide on the left by X, and similarly on the right. And these have to be operations that are inverse to each other. So these left translations and the right translations form a multiplication group, some kind of a permutation group. And in the finite case, just to show you better what these loops are, of course, the multiplication table of a loop is just a normalized Latin square. So you see the identity element in the first row and first column, and then it just has to be a Latin square. Okay, so it's like infinite Latin squares in the infinite case. Now, unlike in groups, you don't need to have associativity, and you don't have to have two-sided inverses. So in general, these loops are very combinatorial structures. They are just Latin squares in the finite case, normalized. So one cannot expect much algebra to come out of that. But there's a lot of space between these combinatorial objects and, let us say, groups. And that's the space that we will explore a little bit from the point of view of solvability. So like in groups, the normal subgroups are just the congruence classes containing the identity element. So there's a one-to-one correspondence between normal subobjects, meaning kernels of homomorphisms, and congruence classes, containing 1. And like in groups, where you measure the deviation from commutativity by conjugations, you can measure also deviation from associativity by these other maps. So TA is just my symbol for conjugation, but LAB, you see what's happening here. I multiply X on the left by B and A, and then I divide on the left by AB. And if I had an associative structure, then this would return X, right? But in a non-associative case, it might not. So this is a deviation from associativity for this pair AB applied to an element X. And similarly on the right. These are certainly elements of the multiplication group because it's a composition of translation. But let's call these the inner mappings, just like we call them in groups inner automorphisms. And you get the so-called inner mapping group. These are no more necessarily automorphisms, but there are still permutations. And just like in groups where we just saw, more or less, that the commutator of the two congruences is the congruence generated by all commutators in the group theoretical sense, we have a similar result that in case of loops, if you look at the commutator of congruences, then it's generated by all commutators and elements that could be called associated. So what happens here, you take an element A in one of the normal substructures, let's say A, and then you conjugate by either U or V, but the U and V have to be related by the other congruence. And it turns out that if you do this for the conjugations and for these other inner mappings, that's all you need to generate the congruence, the commutator of the two congruences, alpha and beta. So it's relatively understandable. Still, the number of terms that you need to consider is very small. It's just 3 types of terms. Now let's have a look a little bit at the difference between the solvability theory I just introduced and the classical solvability from group theory. The classical solvability from group theory makes sense in the loop settings as well. So I just need a concept of an abelian algebra, and an algebra is abelian if its largest congruence, its commutator with itself is 0. In other words, the solvable series has length 1. And it turns out, I'm not going to prove it, that abelian objects in loops are exactly abelian groups. So we don't have to investigate what abelian loops are. They are just abelian groups. And here's the notion of classical solvability from group theory translated to loops. So of course you just have a series, let's say a normal series, whether it's subnormal, normal, it does not matter for the definition, where each factor ui plus 1 modulo ui, so consecutive elements in the series, is an abelian group, right? So that's precisely one of the equivalent definitions of solvability. In group theory, the factors are abelian groups. But now, let me introduce another concept that will allow me to present the congruent solvability in a very similar sounding statement as we just did for the classical solvability. So I will say that a normal subloop X of Q, like Q is some loop here, induces an abelian congruence if the commutator of the corresponding congruence with itself collapses to 0. So I'm a little bit using both notations here because in group theory, the trivial subobject is, of course, 1, the trivial subgroup, while in congruences, it's the 0 congruence. But so this is the 0 congruence, just the trivial subgroup. Okay, so if this happens, then we say that that this normal subloop induces an abelian congruence. And then one can state what congruent solvability means that I just gave the definition. You again have a series, a normal series, but this time you don't want each factor to be just an abelian group. You want each factor to induce an abelian congruence in the larger factor. So qi plus 1 modulo qi has to induce an abelian congruence in q modulo qi. And that's the only difference here. For classical solvability, the factor is an abelian group. In congruent solvability, there is a potentially stronger condition, namely that the factor induces an abelian congruence of the larger subgroup, or larger factor. So this means that every congruent solvable algebra is also classically solvable, and I presented it in loops where it's true in general, but the converse is not necessarily true. So the question is, for which varieties of loops do the two solvability theories coincide? And a related question, in which varieties does every abelian normal subloop induce an abelian congruence? Now let me just remark on this, that if the second property holds that every normal subloop induces an abelian congruence, then of course in the definition here, there is no more any difference between congruent solvability and classical solvability, because the moment you have an abelian group, it would induce an abelian congruence. So if the property 2 here holds, then certainly property 1 will also hold. The two theories will coincide. So that's one possible way of analyzing certain classes. Prove the property 2 that every abelian normal subgroup induces an abelian congruence, and then you know the theories coincide. But it is possible that property 2 does not hold and property 1 does hold. There are examples, easy examples of order A that show that indeed the congruent solvability theory is strictly stronger than the classical solvability. And in fact, you can get quite close to groups. So as an example, I'm just giving something that's called a ball loop, and it satisfies this particular identity. So it's a variation of associativity, not quite associative law, a little bit weaker than that. They are pretty close to groups, but not too close. For example, there is a construction of a finite simple ball loop of exponent 2. It certainly cannot happen unless you are dealing with a cyclic group of order 2. In the case of groups, so it turns out that in this variety that's close but not too close to groups, you still have algebras that are classically solvable but not congruent. So the question is where is really the boundary and what is the principle behind it? So let me talk a little about this question too. When does a abelian normal subgroup induce an abelian congruence? And for that, this can be nicely visualized by the notion of an abelian extension, which is what you would define if I ask you to give this definition. So abelian extension, you have an abelian group and a loop, and it's like a direct product, but you perturb the elements of F of the loop by an automorphism. So some automorphism that depends on R and S here, and another automorphism psi that depends on R and S. And then there's a cocycle. So it's like a little bit like a semi-direct product, but not quite, of course. And then it is very easy to prove that if you have an abelian group that's normally in some loop, then it induces an abelian congruence, which is the condition that says X induces an abelian congruence, if and only if Q is an abelian extension of Q of the normal subgroup by the factor. Okay? So this is how you can spot whether something induces an abelian congruence. You just check whether it's an abelian extension, and then being congruent solvable is just iterating abelian extension, exactly like in groups. And here's the abelian extension visualized, just so that you see what these automorphisms do. So if you organize the multiplication table by cosets, so first the coset of X is represented with 1, and then a coset of X is represented with X, and so forth. Then in a general subsquare, you permute according to phi the rows and according to psi the columns, and you add a cocycle. And there are some normalizing conditions because you are dealing with a loop. So on the boundary, some of these automorphisms have to be identities, and the cocycle has to disappear, as indicated by the diagram. But that's only because you want to have an identity. So let me prove to you, because it's a very short proof, that if you have an abelian normal subgroup of a group Q, then it induces an abelian congruence. So all we have to show is that we are able to organize the multiplication table in this fashion using some automorphisms and a cocycle. And it's easy to do that, so we'll just consider an internal version of an abelian extension. So I have a left transversal U and some elements R and S of the left transversal. Of course, if you multiply them, it's no more an element of a transversal, so URS will be the corresponding element of the transversal in that coset. And this is the form we need to achieve. We need to show that it's like a direct product, but perturbed a little bit. And the calculation is on this one line. So if you do Rx times Sy, then of course I can write Rs S2 minus 1 X Sy, just conjugate the X by S, and then introduce URS and take it away again, and then reorder because I'm in an abelian group, and the outcome is this. So the perturbation of X is by a conjugation. You don't actually have to do anything to Y, it's just identical automorphism. And of course, the element theta Rs is the difference of the representative compared to the product of the two transversal elements, and that's going to be an element in X. So this one-line proof really is a proof that an abelian normal subgroup induces an abelian congruence. And in some sense, most of the area is our fight with our inability to do the same in the non-associative setting. So we would somehow like to reproduce this calculation in a non-associative setting. Well, let me show at least one situation when it's easy to do so. Here's the notion of a nucleus. So the left nucleus are all the elements that associate when the element is on the left, and similarly for the middle nucleus and the right nucleus. And then the nucleus is just the intersection of these three nuclei, so it's elements that associate no matter where you put them. And the lemma that I just showed for groups can very easily be generalized when the normal abelian normal subgroup is contained in at least these two nuclei. Then again, it induces an abelian congruence. Basically, you follow the same argument. But once you go beyond that, it gets more complicated. So the variety I would like to talk about most are Moufang loops that I'm sure all of you have heard about in non-associative algebra. So these are loops satisfying this identity. And of course, the classical example are the octonions, but there are many other examples, meaning I meant to say the multiplicative structure of octonions, of course. And they are very close to groups in the sense that any two elements generate a group. The nuclei are just introduced, fortunately, all coincide, so we can forget about whether it associates on the left or right, it's all the same. And the smallest example, it's not a group, is of order 12, where you double, so to speak, the symmetric group S3. So you can start with any non-commutative group and obtain a non-associative example of a Moufang group by the so-called doubling process. So remember that we have two strategies to prove whether the two theories coincide, and the strongest strategy, which we know will fail in general, is to show that if every normal subloop that is abelian induces an abelian congruence, then the two theories will coincide because the two definitions are the same. Well, unfortunately or fortunately, there are counterexamples to this already in Moufang groups, which is truly very close to groups. And the construction is essentially some vector space with a quadratic form. The details are on the slide. So you take a two-element field, and you have an elementary abelian two group, a vector space, and you have a quadratic form with an associated bilinear form, and then you define a multiplication on f times v according to this formula that uses both the quadratic form and the associated bilinear form. And it turns out that the outcome is always congruence solvable, therefore also classically solvable. It's always a Moufang loop, and it's a group if and only if the quadratic form used in the construction is trivial. Therefore, the associated bilinear form just vanishes. And X, which is one of the two ingredients of the construction, is an abelian normal subloop. And if it's not a group, then the congruence is never inducing an abelian. Then the congruence is never abelian that is induced by X. So in fact, it always fails. So as long as you are dealing with a non-group in this particular construction, you will immediately have an example of a normal subloop that does not induce an abelian congruence. Yet the entire structure is congruence solvable. So I would say the strategy fails as much as it can in the Moufang groups, and at this moment in the slides, it remains open whether the two theories for Moufang groups coincide or not. So a few results on Moufang groups. I try to condense them as much as possible, not to overwhelm you with lots of concepts of loop theory. So here is one concept, a so-called semi-automorphism. And semi-automorphism is something that behaves like a homomorphism, but only on products of the form x, y, x. So you demand that then you can split it into fx, fy, fx. And part of the definition also has to preserve the identity element. And it's then easy to prove that semi-automorphism in a Moufang group preserves order. By the way, orders or powers, rather, powers are well defined because we are dealing with a diassociative structure. So certainly a single element and even any two elements generate the group. And here's sort of an easy lemma. Again, the proof is one line here, which I'm not going to read. But if you have a semi-automorphism of a two-divisible abelian group, meaning every element is a square, then it becomes an automorphism. And as an immediate consequence of this, we obtain the result that if you have a Moufang loop and X is an abelian normal subloop that is two divisible, then every inner mapping of Q restricts to an automorphism of X. So you don't have to, you have now lots and lots of automorphisms to deal with. All the inner mappings will restrict to an automorphism of X. And a few more results, and then we'll put it together for a certain class of Moufang groups. These are results of Gagola, who showed, I don't really need the first result much, so let me focus on the second one. There's a key formula in Moufang groups that relates conjugations to products, and this is how it works. So if you take any elements x, y, u of any Moufang group, then you can express this product in terms of the conjugations in this following strange-looking formula. But what it says is that immediately it gives you some handle on the structure of this Moufang group as long as you deal with third powers. And of course, in general, nothing needs to be, or not everything needs to be a third power. You get stuck with the prime p equal to 3, which is not surprising because in the theory of Moufang groups, the prime p equals to 3 behaves very differently from the other primes. But as long as you can express elements with third powers, it gives you a multiplication formula. So let's go back to the solvability problem in case of Moufang groups. And you can now basically follow the calculation for group theory that shows that if you have a normal subloop that's an abelian group, and it happens to be two divisible, and the entire loop is three divisible, so that we have these formulas at our disposal, then you can manipulate the expression Rx times Sy. I will not go through this again in detail. I mean, these slides will be posted, and that's why I wrote it down, so that if somebody wants to see that, it's there. But basically, you use some conjugations and you use some inner mappings, which we now know induce automorphisms of the normal subloop. And you keep manipulating the expression using Moufang identities and so forth. And I mean, this is maybe 1/3 of the calculation. You continue a little bit longer, and you realize that you can again realize this as an abelian extension. So this Rx times Sy will be expressed in terms of some automorphisms and a cocycle. So when I say you can mimic the group construction, it's much more complicated than in the groups, but still that's something that it's not too bad. And that's because in this case, namely in the case when the Q is three divisible and X is two divisible, the strategy works and any normal subloop induces an abelian congruence. And therefore, as a corollary, if both 3 and 2 behave well, you have a six divisible Moufang loop, then the two theories coincide. It's going to be congruent solvable if and only if it is classically solvable. So the six divisible case is done. Now it turns out that we can deal with the three divisible case as well, which is more complicated, which is based on some characterization of inducing an abelian normal subloop that's in this theorem. So again, a normal subloop will induce an abelian congruence if and only if it behaves somewhat associatively and commutatively with respect to a given u in Q and xy in X. So of course, if this held for all u, x, y, and Q, it would be just an abelian group. But if you restrict the X and Y to X, and U is universally quantified over all of Q, that's precisely when you get that the congruence induced by the normal subloop as abelian. And after much work with this result and using this nice result of Aleš, which generalizes certain results of George Glauberman, one can prove that in the three divisible case, the two theories coincide as well. I will read this result of Drapal because it's interesting. So if you take a finite Moufang group and piece any prime, and you take any subloop, which is a P subloop of Q, then you can look not at the entire multiplication group, but only at the subloop generated by the translations by elements of X. So it's a relative multiplication group. And the result is that this is still a P group. And this is the basic structural result that gives you some foothold on proving this main theorem, that you are starting to see some P groups in the multiplication group, and a lot of group theory then applies. And it gives this result. So in the case of 3 divisible Moufang groups, the two theories still coincide. Let me say a little bit more about the odd order theorem for Moufang groups and some newest results. So this is one of the classical results of George Gladman in the theory of Moufang groups, a generalization of the Fife-Thompson theorem for groups, namely that every Moufang group of odd order is, of course, he said solvable. In this talk, I say classically solvable, because we have these two theories of solvability to deal with. We would like to generalize this and to prove that every Moufang group of odd order, or to strengthen it, it's not just classically, but it's congruent solvable. And the theorem that we need is a deep result of Piroshka-Chergay that says that if you have a non-trivial Moufang group of odd order, then it has a non-trivial nucleus. Remember, nucleus is the subset of elements that associate with everything else. It's always a subloop, in fact. So this theorem says that if you have a non-trivial Moufang group of odd order, it will have a non-trivial nucleus. And you can see that's going to be some basis of an induction argument. I would just like to say a few words about the setting in which Chergay proves, I think, most of her result, because this is a vehicle for translating all of loop theory to group theory. The problem is that the translation is sufficiently cumbersome that on the other side, it leads to problems in group theory that are hard to solve. So often what we do, we have a problem in loop theory and we translate it into group theory and we ask the group theorists and they say, wow, that's interesting, but often they don't know the solution because it leads to different group theory than what you classically find in the, let's say, theory of finite simple groups. So the setup is this, you take all the left translations as a set and all the right translations similarly as a set. And it turns out that both of these are transversals to the subgroup consisting of the inner mappings in the full multiplication group. In fact, they are transversals to every conjugate, not just to the inner mapping group, but to every conjugate of the inner mapping group. So it's so-called stable transversal. Moreover, if you take the left transversals and right transversals, then their commutator lies in the inner mapping group. And finally, I'm not sure if the last line is visible because of some things displayed by the PDF, but what this says that the core of the inner mapping group in MLTQ is trivial. In other words, if you are looking for a normal subgroup of MLTQ that happens to lie in NQ, then there is nothing except the trivial group. And one can show that there is a one-to-one correspondence between loops on the one hand and these types of setups in groups. So you have a group, a subgroup, and certain transversals that behave in a certain way, like so. And that's exactly the playground in which Piroshka-Chergay proves her theorems. And this is a very non-trivial result. It's about, I don't know, 45 pages in the Journal of Algebra. But we can then use this to prove that every Moufang group of odd order is congruent solvable. And just an outline of the proof. So the proof goes by a smallest counterexample. You look at the nucleus, which we know is non-trivial by the result I just mentioned. So if it's everything, then we are dealing with a group, and therefore Fife-Thompson finishes the job. So we can assume it's a proper subgroup, and then you, like in group theory, you find some minimal characteristic subgroup of this nucleus, and you argue on that if you restrict an inner mapping to this minimal characteristic subgroup, it has to be an automorphism, and then you show easily that it's in fact X is an abelian group, and that it induces an abelian congruence. And therefore, by the very first result I think I showed on these slides, that the loop Q is an extension of X and abelian extension of X by Q modulo X. But by minimality, Q modulo X is a smaller Moufang loop of Odd order, therefore it's congruent solvable. And we are done. The entire thing is congruent solvable. Now, let me mention the newest result that we have and the strongest result that we have. It's not yet submitted. I checked the details. I think it's correct, but it's not yet published. So take it with a grain of salt, please. But we think we can prove that a finite Moufang loop is classically solvable if and only if it is congruent solvable. In other words, the two theories truly coincide in finite Moufang loops. In infinite ones, we don't know. And rather than going into the details, which are quite complicated, I will just point out that one of the ingredients that come into play are so-called groups with triality. And these are groups that admit automorphisms, and you probably know these from the theory of non-associative algebras. Automorphisms, let's call them rho and sigma, that generate a symmetric group on three elements, such that certain triality identity is satisfied. And in case of Moufang groups with trivial nucleus, so if the nucleus is trivial, so that's the cases when sort of you get stuck on the induction. If I have a non-trivial nucleus, then I can proceed as I did before, and I'm done by induction. But if the nucleus is trivial, it so happens, then there is a triality on the multiplication group. So the multiplication group again is generated by all the left and right translations, and the triality can be defined, for example, in this way. So the sigma, which is which one is it? That's the transposition, just sends Lx to Rx to -1 and vice versa. And the three cycle sends Lx to Rx and Rx to this particular product of translation, and it all works. So you get a group with triality. If you are interested in these topics, I recommend Jonathan Hall's volume of memoirs of the American Mathematical Society. The title is, I think, Moufang groups and group with triality are essentially the same thing. So that's another way in which you can translate all problems about this case, Moufang groups, into group theory. But again, the problems that one obtains in the triality groups are usually quite complicated. But just to show you that there are many open problems, if somebody would be interested in this, for example, consider recorded in a group, the inner mappings are indeed inner automorphisms, right? They are automorphisms of the group, the conjugation. In loops, that's not so, but there is a nice class of loops, let's call them automorphic, where the inner mappings are automorphisms. And we proved some time ago with Kenyon, Kunin, and Phillips that the Odd Order Theorem holds in automorphic groups, in the sense that automorphic groups of all order are classically solvable. But again, I don't know whether the strengthening is true. I don't know even whether the two theories coincide or not in automorphic groups. So there's lots of other varieties beyond Moufang groups that are very well structured, where this question makes sense and probably leads to interesting problems in group theory. You might think that maybe this could be reduced to the simple case. In case of Moufang groups, the structure of finite simple Moufang groups is well understood. They were all constructed by Page, and Martin Liebeck proved that there are no other finite simple Moufang groups than finite simple groups plus one infinite class of Moufang groups, one for each finite field. In case of automorphic groups, we are in a position that we have no idea if there exists a non-associative finite simple automorphic group or not. We have presented this problem to quite a few group theorists, and they worked on it very hard, and they nearly solved the problem. It reduces to some classification of primitive permutation groups and how they behave. But there are still a few classes that were not covered. So it's an open problem. We don't have an example even of a finite simple non-associative automorphic group. And maybe we knew that none exists. Perhaps that would be another way to look at this problem of solvability. Okay, that's all I wanted to say about solvability, and I have about maybe 10 or maybe 15 minutes max to talk a little bit more about nilpotence. So nilpotence is defined from this commutator theory in exactly the way you would expect using a lower center series. So we use the derived series for solvability, and they'll use lower center series for nilpotent. So you start with the largest congruence and you iterate it, but not in both slots. And an algebra is nilpotent if you reach zero infinitely many steps. And the center is then the largest congruence that centralizes the largest congruence over the smallest congruence. And it so happens that this all nicely coincides with the theory in loops that you would get from groups. The price to pay is that you have to change a little bit the notion of a center, but it will coincide with the universal algebraic notion. So in groups, a center is something that commutes with everything. But here you have to commute with everything, which is in the parentheses here, and you also have to associate with everything. But once this is your definition of a center, which is the correct definition, you have an upper center series and everything works perfectly fine. I would like to point out that even simple questions about nilpotent in loops can be very difficult. And here's an example of it. This is the first theorem that you prove about the inner automorphism of a group, that the inner automorphism group is isomorphic to G modular center, right, in groups. Therefore, in particular, the class of the group is at most 2 if and only the inner automorphism group is abelian, immediate consequence. Now, Brack showed that in case of loops, if the class, nilpotence class of a loop is at most 2, then indeed the inner mapping group is abelian. So that's great. But what about the converse? It was open for quite a while whether the converse holds, and the converse does not hold. Again, Piroshka constructed a loop that the inner mappings commute, they generate an abelian group, but the class is 3. So of course, immediately the question was, well, can the class be bigger? So Gabor, North, and I myself constructed a Moufang loop with this property, so you can get very close to the group and still raise the class from 2 to 3. And it turns out that the answer is no, the class cannot be bigger than 3. And that's a recent result of Michael Kinyon and Bob Veroff, where they proved that if the inner mappings commute of a loop, then the class of the loop can be nilpotent class, can be at most 3. What is notable and why I'm mentioning is that this is a tremendously large project in automated deduction on massive scale, spending about 10 years of work. And some of the proofs that they obtain use about 100,000 deductive steps, which to my knowledge is the longest proofs that have been used in a natural way in automated deduction. Of course, you can cook up some silly automated deduction job that will generate extremely long proofs, but this came out naturally. We still don't know, for instance, if there's a commutative loop with that property that achieves the maximum class 3. And here, as an example, I wanted to show a little bit. This is not from Kinyon and Veroff. This is an older result by Phillips and David Stanovsky, where they prove that the class is at most 3 for certain loops, not all, but certain loops, called Brack loops. Not important what it is. And they found proof by automated deduction using software called Waldmeister. Here's the first page of the proof. These are just the axioms. This is the theorem you would like to prove, and you let it run. And Waldmeister has the ability not only to find a proof, but to generate a PDF that humans can read of the proof. So here it goes. This is the last page of the proof. I'm highlighting the page number. It's page 1068. So there's 1068 pages of calculations using lemmas 2785 and so forth. That establishes this result for that special class of loops. The general proofs are actually substantially longer. Now, the last thing I would like to mention in the last maybe 7 minutes, because the nilpotence really coincides with the notion of nilpotence from groups in loop theory, I would like to say a few words about super nilpotence. That maybe is something that you have not heard about. I certainly didn't before it was brought to my attention by David Stanovsky from Universal Algebra. So here's the most important theorem about finite nilpotent groups. That is that they decompose as direct products of P groups, right? That's the first result. You prove a finite nilpotent group is nilpotent if and only if it's a direct product of its zero P subgroup. Now it turns out that the universal algebraic notion of nilpotence that I just gave, using the commutator theory and the lower center series, is too weak to give you this result. Okay, it's no more true that nilpotent group needs to be a direct product of algebras of prime power orders. But there is a concept that achieves precisely that result, introduced in 2010 by Eichinger and Mudvinsky, called supernilpotence. And let me show you what that concept is. I will need another notion. We have talked about congruence modular varieties. There is notion of a congruence permutable variety. So that means congruence, it's a congruence permutable variety. If you compose the congruences in this way or the other way, it does not matter. So you get the same outcome. And this is characterized by so-called Maltzer term. The variety is congruence permutable if and only if it contains a ternary term that satisfies this particular property. Now in groups, you can verify if you take xy to minus 1z. If I, for example, plug in xy, y, I get xy to minus 1y. That's x. And similarly for yyx. In loops, you can still do that using a slightly different term, like x multiplied by y divided into z. Still works. So these are congruence permutable varieties, which is a stronger property than being congruence modular. And the supernilpotence is defined in that context of congruence permutable varieties using one possible definition is this one. So take a polynomial, which is just a term with constants, and call a polynomial absorbing at some tuple into E if when any of the variables is equal one of these, so then it collapses to E. Okay. So if many of these xi's is equal to ei, then the outcome is E. A prototypical example is a commutator, like commutator of xy, x to minus 1, y to minus 1, xy. Once you plug in identity for x, it all collapses. Once you plug in identity for y, it all collapses to the identity. So you say that algebra is k supernilpotent if anytime you have a polynomial of arity bigger than k that is absorbing, then in fact it has to be constant. Okay, but it's an unusual definition, perhaps, if you have not seen this. There are other equivalent definitions. But the result that Eichinger and Mudvinsky proved then is that if you have a congruence permutable variety, then a finite algebra is supernilpotent if and only if it's a direct product of nilpotent algebras of prime power order. So exactly, sort of, you recover the decomposition result from groups. And what happens in groups? Well, it turns out that in groups, the two theories of supernilpotence and nilpotence are precisely the same. So, and a group will be k nilpotent if and only if it's k supernilpotent. And there are several proofs of this fact. I will give some attributions in a second, just some remarks. So absorbing polynomial, you can normalize the polynomial in the following way, and you can always assume that the absorption takes place from the n tuple of identity elements into one. For example, here is the commutator that I already mentioned, prototypical absorbing term. And it turns out that k supernilpotence always implies k nilpotence, not conversely, but in groups they are the same. And the oldest result I now am aware of, I was made aware of it relatively recently, is from 2008, even before supernilpotence was sort of formally defined. In the thesis of Shaw, who proved that these two concepts, in some different terminology, are the same. And then Eichinger and Mudvinsky proved it, and David Stanovsky and I have a conceptually simple proof that I'm looking at the time and I see that I'm out of time. Let me skip the conceptual proof for group theory. Again, it will be in the slide posted online. I would like to say just a few words about supernilpotence in loops. Now, just like you have a commutator, you have an associator defined by this identity. So it's the element that fixes associativity. And all these terms, as a term, the commutator is absorbing, so is the associator. If I plug in y, let's say 1 for y, then I get xz is xz times whatever, and that whatever, of course, has to be the identity element. So they are absorbing terms. It turns out that for k equal to 1, 2, supernilpotent or k super nilpotent loop is precisely k nilpotent group. So already the super nilpotents and nilpotents for loops deviate for k equal to 2 because there are easy examples of 2 nilpotent loops that are not even super nilpotent, much less 2 super nilpotent. And the result that I wanted to present to conclude my talk is that there is a nice finite basis of identities that characterizes 3 super nilpotents in loops. And there are identities that you would expect, such as associated commutes, and this one says that associated associates, and so forth. But there are some very nice identities, like at the bottom, it says that the associator is a multilinear function, or at least. So in xuv times yuv, xyuv, and so forth. That's the result we have. The question is, what about when k is bigger than 3? We don't even know if it's finitely based. We, of course, expect that k super nilpotent loops will be finitely based, and it shouldn't be hard to prove. But probably it's hard to find a nice basis. And that's where I stop. Thank you very much.
Thank you for your talk. Let me ask you the questions. Maybe in the chat. No. Okay, if no, we'll thank Petr once again. And maybe I ask you to send the PDF of your presentation to us by email.
Yeah.
If you have a presentation without with smaller number of slides.
Yeah, I'll do
like,
that.
Without that pose. Yeah.
Yeah, I have a version that is 1 page at a time. Yeah, the full page. So, all right.
Okay. Thank you.
Thank you.
Okay, thank you for your talk, and so I think we can stop here and see you all next week. Yes, please.